So welcome everyone to this webinar, and I'm Srinath Nair from PDBe team, floating data bank in Europe in EBI. So today I'm going to talk about PDBe Graph Database, which is an integrative knowledge graph for structural data. So this agenda for the session. First, I will start with an introduction on graph and its importance. Then we'll go through property graph model, which is followed by an illustration of where the relational model and the graph model stands. We'll also discuss about the Neo4J, which is a graph database developed by the Neo4J technologies. Also, I would like to introduce the Cypher query language, CQL, which is developed by Neo4J to query graph database. It would be followed by an introduction to PDBe Graph Database, as well as the visualization component to see the PDBe Graph Database schema. Then we'll be going through the PDBe Graph API, which is a REST API that is powered by PDBe Graph Database. At last, we'll be going through few examples and see how graph database can be used to solve some of the scientific questions. So what is a graph? It's a data structure or a model which depicts connection between nodes. What Wikipedia says about graph theory is they are mathematical structures that can be used to model pairwise relations between objects. A graph in this context is made up of vertices, which are also called as nodes or points, which are connected by leg edges, which are also called links or lines. Why graphs are important? So today's data set has got complex relationships. So relationships are equally important as the data itself. And considering relationships as first-class like elements helps in fast querying of patterns in the vast array of data. And another benefit is its semantic clarity, as it stores each and every detail of the data in nodes and relationships, which helps to discover and model like any kind of relationship that you have as a graph. Another benefit is the no schema feature, which helps to easily add new kind of data. So let's see where relational model and graph model stands. So how do you represent an entity or a real world like object in a database? On one hand, we have the relational model, which uses a ledger style structure. So you'll have data represented in a table with columns as properties and rows as each record. Then we use a foreign key constraint to create relationships between tables. But when we try to create relationships of real-world data, the relational database becomes more complex and rigid, which needs multi-table joins and complex queries. The primary and foreign keys in relational database are not enough to handle these extensive connected data. Due to their underlying design and storage implementations, it will require costly programming to query these data. And on the other hand, we have the graph model, which is much simpler. It uses nodes or vertices to represent an entity and relationships or edges to create connections between them. Also, it is the whiteboard friendly. So typically, while designing a data model, people would draw example data on a whiteboard and connect the different objects to denote their relationships. In case of relational model, this structure needs to be reformatted to fit the normalized relational tables. While in graph model, this model stays the same as drawn on the whiteboard. What is a graph database? Graph database is a database which is designed to store and retrieve data in the form of a graph. It treats relationships as equally important to the data itself. It uses nodes to represent an entity and edges to create connections between them. To get the data fast, it is very important to reach to the starting node as fast as possible. For this, we can create index on these nodes, which helps us in faster lookups. So let's talk about property graph model. The property graph model is an approach in graph database design. The foundation of this model is based on nodes, the relationships and properties. Nodes are used to store entities. It stores data as attributes called properties, which are key value pairs. Nodes are categorized as labels, which basically depicts the type of data the node is storing. It is also used for storing the metadata, like the index, constraints, etc. The labels are used to tag each node. In some cases, there can be multiple labels as well. In the case of the given example, there are 3 entities which are represented as nodes. And we use some labels to tag them, which are basically the employee, company, and city. For instance, there would be some employees who are the managers. So we can actually tag those nodes with manager label as well. And on the other hand, the relationships are used to create connections between nodes. Like nodes, the relationships can also have properties. A relationship should have a starting node, an ending node, a type, and a direction. From the previous example of employee, company, and city nodes, we can use the relationships to create connections between them. So here, works in relationship is used to denote that an employee works for a company. The data specific to this connection, which is the sales property, like in this case, which can be used to store the very data that is specific for this particular kind of relationship. And it is also possible to have any number of relationships between same set of nodes. For example, in case of the relationship between company and city nodes, the located in relationship can be used to depict the location, and headquartered in relationship can be used to denote the headquarters of the company. So let's talk about Neo4J. The Neo4J is a graph database which is developed by Neo4J Technologies. It is a native graph database, which means it stores data in the same way we see the data. It delivers consistent and real-time high performance on a large interconnected data. It is a NoSQL database which doesn't use the traditional tabular structure for storing data. Neo4J implements property graph model which we discussed, and it is whiteboard friendly. And few things about Cypher query language. So the Cypher is a query language which is developed by Neo4J, which can be used to store and retrieve data from the graph database. It's a declarative language that works with graph database for reading and writing, which means it helps us to ask what data we want and not how we want it. It is developed to be more human readable and can be easily used by non-developers like analysts and other operational specialists to answer their specific queries. And also it is open source and is part of the Open Cypher project, which aims in implementing Cypher and in other systems. Going back to a simple example of employee, company, and city, this Cypher query is used to create the respective nodes and relationships. And Neo4J browser is a user interface for working with Neo4J, which is available as part of the Neo4J graph database. By using this, you can query, visualize, and administer and monitor your Neo4J database. The results for your query can be interactively visualized in the Neo4J browser graph view. And also at any point of time, you can click on any node or relationship to see the respective view and of its properties. So why did we choose graph? PDBe data itself is inherently tree-like structure. So you can conserve each PDBe entry as a node, which are connected to PDBe chain and entity nodes, which are then connected to the PDBe registry nodes. So annotations are really important to find solutions for a biological problem. At each level of organization, there are relevant annotations which are required to get more clarity on what is going on behind the scenes. We have diverse types of residue-level annotations. To solve some of these questions, it would be essential to retrieve different types of annotations for a residue, which in relational database needs complex joins on multiple tables, which are expensive. Graph databases proves to be an efficient way of storing and retrieving these kinds of data, as there is more emphasis on the relationships than the data itself. It also helps us to find some interesting patterns, which could be valuable information for the users. With the foundation of our sister resource, PDBe-KB, we gather huge number of the residual level annotations from our KB partners. The motivation behind PDBe-KB is to create an infrastructure for structural and functional annotations of PDBe entries based on FAIR principles. Just by integrating KB data with core PDBe data helps in answering some specific scientific questions. We currently have a variety of annotations for PDBe residues. This includes sequence and structural domains like interpro, scope, cat, etc. From the interactions point of view, we have small molecular interaction data from RPGO, protein-protein interaction data from PISA. Also, there are validation data available for PDB residues. This data is more enriched by annotations from PDBe-KB partners. Some of these annotations actually include a predicted and curated ligand binding sites, catalytic sites, PTM sites, and many more. We have a process called SITS, which provides the residue level mapping between PDB and UniProt entries and storing the PDBe-KB data as a graph offers great benefits, in particular by allowing straightforward the transfer of these annotations between PDB entries which map to the same UniProt accession, as well as to the highly similar the UniProt accessions as well. So this is how a node is represented in Cypher. It is enclosed in parentheses. So here the word entry refers to the node label, which means we are looking for or referring to a node of type entry, and E is a variable which can be used later to access the node. As we have seen before, nodes have labels. So in this case, it is entry. Also, nodes stores data in the form of properties, which are key value pairs and are enclosed in curly brackets, and inside a node pattern. Now we have nodes, and we want to create connections between them. This is done by using a relationship, and the relationships should have a direction. And also, what makes a relationship meaningful is its type. The same pair of nodes can be linked using many types of relationships, and specifying the relationship type in the graph pattern match helps in getting the exact data that we are looking for. And similar to nodes, the relationships also store data in the form of properties. So let's talk about some stats on PDBe Graph Database. Currently, we have about 1 billion nodes, close to 4 billion relationships, and more than 4 billion properties. It comes to about 450 gigabytes of data on disk and is still growing. We load the database as part of our weekly release process and distribute it on the public FTP to be used by the community. You can find more information on how to download the PDBe Graph Database by using this link. Next, we will discuss about the graph schema visualizer, which can be used to understand the underlying schema of PDBe Graph Database. To better understand the data, it is important to have an easy way of conveying the schema of the database. So we developed a visualization tool which helps in an effortless and effective way of exploring the database. And you can access the schema visualizer by using this link. The graph schema visualizer is a web-based visualization tool which has 3 sections. And on the left side is the list of node types that are present in the database, which is more descriptive and not the actual label used in the database. So there is a filtering text field which helps in searching for the information the user is looking for. The second section is a middle section, which is actually the visualization component. And the third section is on the right, which is basically the information box. It gives the text description of the item which is selected in the graph. If user is interested in interactions, then enter interaction in the text field, and it should fetch the nodes that are related to that keyword. Then if you find a result of interest, you can click on it to see the visualizer, like in the middle section. For example, if the user is interested in interface, then click on interface, which will take you to this view. Now this loads the graph which is related to the selected interface node, which gives nodes directly linked to it, its outgoing and incoming relationships as well. The nodes can be dragged and arranged as per the convenience. And in the info box, which is on the right side, details of interface node can be found. It gives information about the actual label used in the, which is defined in the database for this particular node, a description like about the node, its incoming and outgoing relationships. And also, we started adding properties of nodes and relationships in this section, and we are rolling out them to other nodes and relationships. For instance, if you look for atom node and click on the atom node, and on the right side, there's a property section which gives a text description of each property that is defined in that node. Another useful feature is expanding the relationships from nodes, which help in exploring the database much further and finding how the nodes are related to each other. Going back to the example of interface, it would be interesting to know what are the connections of PDBe residue nodes. For that, you can click on the PDBe residue node in the visualization component, which expands the view by displaying its connected nodes and relationships. So like this, you can drill down much further by clicking the nodes of your interest. At any point of time, you can always go back to the previous state by clicking on the previous button, which is part of the controls. The view can also be reset using the refresh button on top right. This would be especially useful when you try to expand more and more, and you will end up in getting a messy visualization. So you can always use the refresh view, or you can always the selected node and drag it as per your convenience to make the visualization more clear for you. And also similar to nodes, you can view the information of a relationship by simply clicking on it. So here, if you click on has PDBe residue the relationship, then you will be able to see the details on the right side in the information box. PDBe Graph API is a RESTful API which is powered by PDBe Graph Database. It currently serves close to 80 endpoints. API documentation can be accessed from this view. Graph API serves as the source for our aggregated views and recently released COVID-19 pages. You can use this link to get more information on that. So this is a web-based documentation where you can get details of all endpoints that are exposed by Graph API. For example, if you're looking for interface residues for a protein, you can search for interface in the text field and click on get interface residues for a UniProt accession. This will take you to the section which provides a description of each code and a URL which can be used to access the service. It also provides you some information of the parameters that should be used to access the service, and also description of the fields and in the response if you get a successful response. It also provides a way of sending a sample request and check the response. You can enter your protein of interest in the text field and click on send. This makes an API call and the response will be rendered on the page. Now let's see some examples. If you want to find all ligand binding residues for a protein from all PDBe entries, you can make use of this API call. So in this API call, the only parameter that you'll be using is the UniProt accession, which will give you the ligand binding residues for that particular protein. This simple Cypher query is used by the API to query the graph database to fetch the respective data. The first part of the query is used to fetch the bound ligands for all the residues of UniProt accession PO-DT-D1, which is the replicase polyprotein found in coronavirus 2. Match clause is used to denote that we are looking for some data in the graph. It is similar to the select clause in the relational database. Once we traversed through the data we want, you can use the return clause to return the results. In PDBe Graph Database, we store every UniProt accession in UniProt node and connect them to its UniProt residue nodes by using the pass UNP residue relationship. We also transfers bound ligand annotations from PDBe residue nodes to the mapped UniProt residue nodes using bounded by relationship. So by using this, it would be very easy to fetch the ligand binding residues for a UniProt. And another example to fetch all residues of a protein from all PDBe entries which take part in protein-protein interactions. This API code can be used to get the data. This is a Cypher query which is used in the API to fetch the relevant data. Similar to bound ligands, we transfer the protein-protein interaction data from PDBe residues to their mapped UniProt residues as well. This data is available in interacts with the relationship between a UniProt residue and its partner. Now let's see some scientific questions and see how PDBe Graph Database can help in solving those. The first question could be from the small molecules. The question would be, is it possible to find ligands which have the same scaffold and interact with the same binding sites? The answer would be yes. Yes, we can provide it. Also, we would be able to add more information to this, like are these binding sites annotated as catalytic sites? Are these ligands like identified as drugs? What are the conservation scores for these shared binding sites? This is a simple example of similar small molecules. We have erythromycin and clarithromycin, which are antibiotics, which share the same scaffold and are bound to the same binding site in two different structures of an aminoglycoside phosphotransferase. With the help of this simple Cypher query, we would be able to get the similar ligands and their shared binding sites. So using the graph from the previous slide to get more understanding of the Cypher query. The first match clause is used to get the similar ligands having the same scaffold as clarithromycin. So we will start with chemical component node. So that is how the ligands are represented in PDBe Graph Database. We'll start with this chemical component node of clarithromycin to get the scaffold using contained scaffold relationship. Then we use the same contained scaffold relationship to find the similar chemical component nodes. Now we have pairs of chemical component nodes, and we use the bounded by relationship, which we discussed in previous slide, to get the shared binding sites of these ligands. Now with this data in hand, it can later be expanded to answer other interesting questions. Another interesting question could be related to disordered interfaces. Is it possible to find macromolecular interaction interfaces which have highly conserved residues and are also like annotated as disordered regions? The answer would be yes. We can provide the data. Also, we can give like more information to this. Like, are there any non-domains in these interfaces, as well as any secondary structural elements? This is an example of such a case of an amino acid which is annotated as to be disordered, as well as highly conserved, and are found taking part in protein-protein interaction. A simple Cypher query like this can be used to get such a valuable information. And in this query, the first match clause is used to get all unipolar residues which are annotated as disordered. We use IDP region property in a uniprot residue node to store this data. Now, with all these residues into several regions, we get all of their interacting partners using interacts with relationship, which we discussed earlier. Now it's just a matter of filtering these residues based on their conservation scores. Also, another interesting question related to variants. If you want to examine the structural effects of mutations, it would be interesting to know every pair of PDBe residues where one of them is a wild type in one PDBe entry and a variant in another PDBe entry. We can provide this data as well as other valuable information for these residues also, like are they part of protein-protein interactions? Are there any ligands binding to them? Also, are they conserved, buried, like accessible, or intrinsically disordered, etc. This is an example of such a case. Here, the engineered aspartic acid and its wild type glutamine and all the mapped annotations for them. The single node in blue is the engineered aspartic acid, and the many blue nodes, which are the wild type glutamine, which are mapped to the same UniProt residue here. All these nodes in green, gray, etc., are the different types of annotations for this engineered like residue, which are available in the PDBe Graph Database. Now let's see the Cypher query, which is used to get such a data. The first match clause uses map to UniProt residue node. So it uses a map to UniProt residue relationship to find the PDBe residue pairs that maps to the same UniProt residue. So this data we get from the SIFs. Then we apply filtering on these PDBe residue pairs on their ChemCompID property to find the engineered and the wild one. With this data in hand, it is now possible to expand it to other relationships or expand it to other annotations, like its sequence and structural domains, bound ligand interactions, macromolecular interactions, etc. These are some of the interesting data that we have in the PDBe Graph Database. There are more materials which we compiled that can be used to learn about PDBe Graph Database, its schema, some use cases, etc. Also, these useful resources can be used to learn more about Neo4J, Cypher, graph modeling, etc. So before I finish, I just wanted to let you know that we have some open positions available. Like if you're interested, you can view our jobs page to find out more. So thanks for listening to this webinar. With this, I would like to stop here and open the session for questions.
So we already have one question for you, Srinath. It's from Rishikesh. So can we get information about mutations from a domain providing the list of PDBe accessions? And if yes, how?
Thanks, Rishikesh, for this question. Yeah, this is yes, but I would like to get more clarity on it from my colleague David, who can help me in filling out the data part of it.
Sure. Yeah. So all that data is available. I think through the API, the Graph API, you should be able to get mutations per PDBe entry and also domains per PDBe entry. I'm not sure whether you can package it into one single query, but between the two queries, you should be able to get that information.
Question from Grigor. Can we find information about ligand binding site from homologous structures?
So yes, it should be possible. I don't think there is a single API call which can give you this information, but you would be able to use the ligand binding site code to get the ligand binding sites of and also the homolog structures. So there is a PDBe section like under the Graph API documentation where you can get the information about the ligand binding sites for a PDBe entry, which could ideally be used by this.
Yeah, just an additional point, I guess, on top of that is, depending on how you're defining homologous structures, there's various ways that we do that. So one of the things we do is get uniref 90 information from Uniprot, which shows all the other Uniprot IDs that are within 90% sequence similarity. But obviously we also have domain information, which highlights similarity as well. So defining how you want those homologous structures to be linked is the first step, and then you should be able to find that.
Can you highlight a query example that can't be done using the ordinary relational database?
If I have a single residue of my interest and I want to get over the whole set of annotations for it, the way in which I would be doing is by joining a set of multiple tables. So for example, if I want to get the sequence domains and the structural domains, I would be having those tables for cat, scope, and interpro. And also, if I want to get the binding sites for a particular residue, then I'll have a separate table for it. And if you are asking for a Unipro residue, we have to basically get to the PDBe residue, the data which is provided by the SIBs, which itself is the residue level mapping table itself is a very huge table. Now with all this in hand, it would be a complex join on all these tables, and it would require a lot of time to query this data. But by using the graph, it would be pretty easy to get this data.
Question from Amrita: can we learn about protein-protein and protein-drug interaction?
Yes, you should be able to, and I think David can give more information.
Yes, so this is something we're already doing on our PDBe-KB protein pages. So here we highlight for a particular Uniprot protein all the PDB structures that exist and all the interaction sites for ligands, so potential drug interactions, and also protein-protein interactions, and they're all highlighted there. So this is all done through the graph database. We also have information about drug bank IDs as well for the ligands in the PDB. So if you're specifically looking for certain drugs, you should be able to query that as well. So yes, that's definitely feasible.
Another question from Gregor: how can we change identity percentage to find information about ligand binding site from homologous structures?
So in terms of our uniref 90, at the moment we only have a 90% sequence similarity. However, one thing we do is we also have a clustering mechanism to cluster PDB sequences throughout the database. And there we have different identity thresholds for that. I'm not sure 100% exactly where you'll find that in the API, which API call it is, but we can certainly clarify that and let you know. But yeah, I think the thresholds we set there are something like 40, 50, 70, and 90%. So that would, I think, be more like what you're looking for. But at the moment, we can't do that as a dynamic percentage identity.
Question about Cypher: does this Cypher query language stores almost everything that could be computed from PDBe file, or do we need to do calculations as per need again?
So the PDBe Graph Database is a graph, like it's a database, which is very similar to other kind of database systems. So basically, we store the data in the form of the nodes and relationships, and the Cypher query is actually used to fetch some data, from this database. Now, I think as per my understanding, most of the PDB, like most of the data that is available like in the PDB file or like in the MMC file is available in the PDBe Graph Database. And you will be able to use the Cypher query language to fetch those data. And I don't think it should be considered as an alternative for a whole PDB file or an MMC file as such. So it should be basically, it should be ideally be used to query some interesting like questions that you'll be having, or if you want to find like if you want to find some interesting patterns like in the data, you could make use of the Cypher query language. So it is very similar to the SQL language in like in Oracle database as well. Okay, so do we need to do calculations as per the need again? So that's the second part, right? Yeah. So it all depends on your use case or on your question. So basically, if there are some post processing that should be done after getting these results, yeah, there are many functions and procedures that are available in Cypher which can be used to aggregate the result that you have, and you can make use of them to actually to mend the result as per your need, or you may need to do some post processing from Python or Java or something like that, and to produce the results.